Hello and welcome to week one of ELEC50B. We're going to start our discussion this semester with the sine wave, and then we'll talk about frequency, period, wavelength, phase relationship, and then some non-sinusoidal waveforms like a square wave or a sawtooth. And then we'll end this chapter talking about harmonic frequencies. Now, each week we'll have a video where we'll cover the material, and then every week we're going to have a homework assignment. So I'll cover some of the homework material as well, what you needed to know for that. All right, so let's jump in here. Now, we use AC to transfer power, and then almost all of our equipment, all of our utilities, our computers, our cameras, our TVs, they use DC, right? So like in the first semester class where you took ELEC50A, that was focused on DC with, the uh, Ohm's law and power transfer theorems, Thevenin's and superposition. And all of that was very, very instrumental. And all that it still applies. But now we're going to look at the power that is from AC. And one of the best way to, if someone asks you, well, why do we use AC? Where is AC used? Well, it's in our power distribution, right? So the power coming from where it's generated, whether it's a dam or a nuclear power plant or a hydropower plant, whatever it might be, solar, it's going to come in the form of AC to be transmitted to our homes, and then our devices will convert it into DC. Now, remember, if you remember some of the labs from DC, you use the trainer or a DC power supply or a battery, right? And DC power is really a one direction where the current is always flowing in one direction, right? So let me we'll just say it that way. All right. So AC was created shortly after Thomas Edison started the electrification of the American homes, and he used DC. And there's a video, if you go into the week one module, I have a Tesla versus Edison or Edison versus Tesla. And it shows a video from the History Channel with the men who built America. And it's an episode that focuses on Edison and Tesla, which is really DC versus AC. And AC, Edison, um, he was a great inventor, but he was also kind of a scoundrel of a guy. I mean, he did not want to lose anything. And so they came up with this idea of showing how dangerous AC was. And if you watch the video, there's a part where they actually electrocute an elephant using AC and show how dangerous it is. But so DC was first, and then AC. Now, one of the main problems with DC is that you have power loss over distance. And remember, one of the formulas for power is power equals current times voltage, or pi. And if you substitute voltage equals current times resistance, if you substitute that in, you get power equals I squared R, which means over distance, there's going to be a lot of power loss. All right. So what we have to look at here is at very high voltages, we want to reduce the amount of power loss by decreasing the current. So if you have a really low current and then a really high voltage, you still have the same power. So that's where uh, transformers come into play. And we'll talk about transformers here in more detail later. But the transformer lets us have really high voltage at really low current. And then when it comes into our homes, it transforms back into high current and relatively low voltage. Okay. So that's one of the key things here. So with the transformer, here's our power plant. It goes through a step up or step down transformer, which really a transformer is going to take the voltage and the current ratio and switch it from high voltage, low current to high current, low voltage, or vice versa. So in this case, it's high current, low voltage, and it's stepped up where it has high voltage, low current. It comes into our home, it gets stepped down again into a low voltage and a high current. Okay. And that happens all over the place. Now, one of the things that's very common today um, is you don't see overhead power lines, right? If you've paid attention to the news over the last several years, there's been a lot of wildfires caused by these overhead power lines. And, Edison and LA Water and Power, and then whoever provides power in the northern part of California, they've all been sued. And they've really made an effort to get rid of these overhead power lines, because if something happens, lightning, wind, whatever, and these lines drop, they can start a fire. So the underground power lines are very common. And then another thing, I just saw an article the other day where they showed this guy climb up a power pole, and then he must have had some electrical background because he didn't get electrocuted, and he cut one of the lines and it dropped down. Then he climbed up the other pole and he cut it, and he did it because they're stealing the copper in the cables. So, crazy world we live in right now. But that's another example of that. All right. So when we use the term alternating current, that's a very good descriptive term, because the current is actually alternating, right? And we'll see that here in just a minute. And the other thing is it's not only is it alternating its values, right? It's going from a negative or a zero voltage up through its positive value, then back down, and then it comes back up. It's also alternating its polarity. So it's going positive, right? It goes up to positive, comes down to negative, goes back up to positive, and so forth. So, and it's doing that in at a regular interval, which is known as its frequency. Okay, so we're going to define and start throwing some terms at you here in a little bit. But the amplitude is how high it goes for each half cycle, and then it reverses polarity and goes from positive back down to negative, back up to positive and negative, and it does that on a regular basis. Whereas with DC, remember, it's consistently, it's a static level, or a stationary value. All right. So with our AC, we're going to talk about a device here known as the oscilloscope. And this is going to be probably the main piece of equipment that you're going to utilize this semester. And you're going to become very, very familiar with both the digital oscilloscope and the analog oscilloscope. And the oscilloscope, now remember, if you think back to DC, we use the multimeter, right? The DMM, the digital multimeter, that used primarily in all your labs. And it would measure the value, and you'd get a digital output, or you'd get the analog meter that would show the needle would move to indicate the value. And that's a measurement device, whereas the oscilloscope is a visual device. So it's going to have two axes, right? We're going to have a vertical axis, right, which is the vertical is up and down, and then we're going to have a horizontal axis. And the vertical is going to be normally, and I say normally because sometimes we'll use it for current, but almost always we're going to measure voltage. So the vertical scale here is for the amount of voltage. And then the horizontal is our time. And one of the things that we're going to become familiar with is the calculation for determining the frequency is you just take the inverse of the time period, okay? So for example, here we have 16 divisions and we're on 1 millisecond per division. So it goes from here to here or any place that's equidistant, right, on the sine wave. If it's 16 divisions at 1 millisecond, the period is 16 milliseconds. And then if you take your calculator and take 1 over 16 times 10 to the negative 3, you end up with 62.5 hertz. Okay? So that's how you end up getting or calculating the period. All right? Now, the device that we're going to use to generate the frequency in the signal will be the frequency generator. Okay, so that's a device that we have in the lab, or you'll sign up from the stockroom, and you set that up and you program it so that it's, if the lab says a 10 millivolt peak to peak at 100 mega or 100 kilohertz, you would set that up and then put that into your circuit, and then you would put your oscilloscope probe on the input, and you would see it on your screen here. In the first lab, the first 2 labs you're going to do in the first week of school during week 1 are to familiarize yourself with the oscilloscope and the function generator, right? And you can see it, but it's not exactly like this picture here, but very, very similar, okay? And you'll get plenty of practice throughout this course working with that, all right? Now, AC can be converted to DC, and it's done all the time. If you have a computer and you turn it off and then open up the power supply, you'll see inside of the power supply, it will come in as AC from the wall, and then it's converted from AC to DC using a bridge rectifier circuit and some filters. And we'll talk all about all this stuff as we go through. But if you're in the electronics major, the electronics device is the ELEC50BWeek1, which some of you may be taking that this semester or you're taking it next semester. It's all about the diode, the bridge rectifiers, and then all kinds of stuff, right? The transistor and various things like that that are all used for converting it. All right. All right. So let's kind of back up a little bit, and I'm going to switch my camera here real quick. All right. And hopefully you can see this screen here. But if we have a sine wave, so let's just say here's our time. Remember, that's our horizontal axis. And then here's our voltage. Okay. And if we have the amount of time, so let's just draw a sine wave here, and forgive my artwork here because it's kind of tough to draw this really nice, but that's not too bad. So this is our 0 volts, right? And then just for the sake of argument, let's say this is plus 5 volts and minus 5 volts. And then let's just say this right here is at this point here is 1 second. All right, so 1 second. So if we were to describe this sine wave, there's a couple of things we would look at. First off, we would want to say, what is its amplitude? And the total amplitude is from the highest point to the lowest point. So from here to here. And because it's going from peak, so this would be voltage peak, and that's a V, not a U. Let me make that a better looking V. And then this is positive voltage. This would be our negative voltage peak, okay? So in this case, we would say the VP is 5 volts, right? So this peak goes up to 5 volts. This peak goes down to negative 5 volts. The voltage peak to peak would be this one here. And that would be a total of 10 volts because it's going from, it goes up 5 and down 5 for a total of 10 volts. All right. And then the other thing we would measure here, get my markers organized a little bit better here, would be the amount of time it takes. So here we would say it goes through one complete cycle in 1 second. So the time or the period would be 1 second. So we'll say the period is 1 second. And then remember the formula is the frequency equals 1 over the period, which would equal 1 over 1 second, which would be 1 hertz. So the unit for frequency is hertz. So like, for example, if you were to, and for those of you that aren't aware, I teach primarily, most of the classes I teach are in the CNET program, right? The computer networking technology program. So we're always talking about computers. So where we see the frequency all the time is like with our memory or with our CPU, the processor, right? A 3.4 gigahertz processor, which means it can, if the frequency is 3.4 gig, which is 10 to the 9th hertz. So what would be the period? It would be 1 over the frequency, which would be 1 over 3.9. So let me show you the calculator here. And this is the same calculator that you need this one for the class. You probably have this for when you bought the DC stuff. But if you go 3.9 and then exponent 9, hold on, I said 3.4. Let me clear that. So 3.4 to 9, that equals 3.4 gigahertz. And then I want to take the inverse of that. So if you just do the, let me get familiar with this calculator again. So if I take 1 divided by my answer here, it's 1 over that, which would be 294, and then into the negative 12th, which would be, it goes milli, micro, pico, and then nano, then pico, right? So it's 294 picoseconds, right? 10 to the negative 12. So that means that if we were to draw this here, if our frequency was 3.4 gigahertz, and that's what our processor operates at. This time here would be 294, about 294 times 10 to the negative 12 seconds, which is super fast, right? So it just kind of puts things into perspective. All right. So when we look at that, so I'm going to switch back to my PowerPoint. And this is the problem with sharing with PowerPoint, is you have to go back to slide 1. But let's go back to where we were here. And so that's the amplitude, the frequency, and then the phase. We'll talk about the phase here in a moment. But the thing that is important with all of this is that it can be that all of these attributes can be transmitted over our lines, our power lines. Okay. Now the sine wave is the most common, and the sine wave is what a generator produces, or an electronic oscillator. And power generation, for those of you that aren't aware, I've spent 4 years in the Army, and my job description, my MOS, my military occupational specialty, was 52 Delta, which was a power generation equipment repairman. So I worked on generators for the 4 years I was in the Army, and all the way from little tiny generators, kilowatt, and then all the way up to the really big 100 kilowatt diesel generators. So, and so power generation, it is how most of our electricity is created. So if you go to a dam, like say you go to the Hoover Dam or any dam that has a tour, you walk through and they'll show those big turbines that are turned by the power of the water, and it's generating power with the rotor and the stator. Okay. Now, naturally, there's all kinds of analog devices, if you will, that are found in nature. Our vocal cords, our eyesight is an analog device that can pick up sine waves, right? It all produces sine waves. Very, very common. Okay. Now, the term sine wave is also from trigonometry. And I don't mean to scare you with any of this math, but the trig, right, with the sine, the cosine, and the tangent are the most common ones that you see there. And it's the same concept that we're going to talk about in our class here. All right. So the amplitude of the sine wave is not constant. Therefore, there are a variety of ways used to describe it. And we say it's not constant because the value, the voltage is changing, right? And remember, our vertical is our voltage. So it's going from 0 volts to 1.5, 2.5, 5, -5, all the way, right? It's constantly changing over time. And that's what the oscilloscope does. It shows us our voltage and time constants. So it will give us that understanding. All right. Now, the term peak is referring to the point on the sine wave of maximum amplitude. And then it's either as the maximum or the peak value, which will be normally in our textbook, it will be referred to as VP. And then if you see peak to peak, it's VPP, okay, with the capital V and then the underscore PP, okay? During each complete cycle of AC, there are always 2 maximum or peak values, one for the positive half cycle and the other for the negative. And then that distance in between is voltage peak to peak, all right? So this is a good graphic that kind of shows it there. All right, so that's our amplitude. That's our voltage level, is on the vertical axis here, all right? So if you were to see something that you have to convert from voltage peak to voltage peak to peak, voltage peak is half of the peak to peak, right? So obviously this value here is 1/2 of this one. So if you know what the peak to peak is, you divide by 2 or times 0.5, and that gives you the voltage peak. And vice versa, if you know the peak, you just double it and you got the peak to peak. All right, so those should be really easy calculations. And then the current is the same thing. The current peak is 1/2 of the peak to peak current. And then the current peak to peak is twice the current from the peak. All right. So those are really simple factors that you should be able to work with very easily. All right. Now the thing is though, when we use our our oscilloscope, we see things in peak and peak to peak. When we use a meter to measure it, it's going to have the RMS value or the average value, okay? So the true average value of a sine wave is 0. So, and this isn't a math class, so I don't want to get lost in some of this. But remember, on a sine wave, the value under this part of the curve equals the same amount of the area under the curve equals this area under the curve. So the total area under the curve, if this was negative and this is, or this is positive and this was negative, when you add them together, you end up with 0. So in the true average value of a sine wave is 0 because the waveform has the same amount of positive above 0 area and the negative below 0 area. Thus, the net area is 0, which makes the true average 0 over the complete cycle. Okay? So graphically, that's how you would describe the average value is going to be 0. So to an AC load, the direction the current flows through the device doesn't matter. Whether it's going positive and then negative or whatever, it doesn't matter because power, remember, is the current times the voltage, and power is the amount of work that's being done. And remember, power is dissipated in the amount of heat generated. Okay, so P equals I times E, and that's true whether it's AC or DC. Now, for AC, the average value is taken as the average of all the instantaneous values during 1/2 cycle. Okay, now the average value of a sine wave is the voltage peak times 0.637. Now, the term DC value, this is the DC or average, is often used to mean the average value. So this is important. If we were to take our sine wave here, and let's go back to our oscilloscope picture, and if we were to put our oscilloscope on, it would look like this. If we took our DMM and put it to AC voltage and read it, right? Now let's look at how many total. So we're on our voltage, we're at, well, it doesn't show the voltage division, but let's say we're here, we go 1, 2, 3, we'll just do peak, we'll go 1, 2, 3, 4, 5. So if this is at 1 volt per division, that would be 5 volts peak. So, but if we put our AC meter on there and we measured it, it would be 0.637 times 5 volts. So that would, our meter would be 3.185 voltage. That's what it would say on our meter because it's doing the average. Okay. Now, it's important that we understand that our meter is going to give us a different value because it's calculating it different. The sine wave shows it exactly like it is. The meter is going to show us the average value. Okay, so here here's a problem that's in the textbook. It says determine the average value of a positive alternation whose maximum amplitude is 200 volts. So you just say 200 times 0.637, and it's 127 volts. If we put our oscilloscope on there, it would show 200 volts. If we measure with our meter, we would get 127.4 volts. Okay, so keep that in mind. Now, the effective value is the most common value or most commonly used value for an AC waveform. And this is the value of AC that has the same heating effect on a resistance as the same DC value. Okay, so expressed another way, the effective value is the equivalent DC heating value of the AC. And for example, an AC sine wave voltage whose peak is 170 volts has an effective value of 120 volts. When this source is connected to a certain resistance, it dissipates the same amount of electrical energy heat as a DC voltage of 120 volts. So if we put a DC battery on that same resistance at 120 volts, it would generate the same amount of heat as an AC sine wave at 170 volts. Okay, so again, and I know that I say this a lot, but keep that in mind as we go forward. Stick that in there. All right. Now, the RMS, which is the root mean square value, is found by squaring the instantaneous values, adding these values, then dividing by the number of values. So remember, the mean is all the values, and then divided by the total number, the sum of the values divided by the number of values. That's the root mean square. So mathematically, the voltage RMS is 0.707 times the voltage peak. Now remember, the voltage average is 0.637 times the voltage peak. VRMS is the 0.707. Okay, so that's where you would get that. Now to convert it back, if you take 1 over 0.707, which comes out to 1.414, you multiply that times the VRMS, and that will give you the voltage peak. Okay, so there's just some other ways of doing this. So let's look at this example here. If we know that we have 2.828 voltage RMS, what's the VPP? We just take it times 0.707 and we get the value. Okay, and away we go. So if the peak value is 350, we multiply it times 0.707, we get VRMS. If we want to go VRMS, we divide by 1.414, and we get the voltage peak, right? So you can see how that works there. All right, so let's talk about this from this graph. So again, we have the peak value. We have the peak to peak would be from here to here. Our time is our period. 1 over the time is the frequency. Our effective voltage, or our VRMS, is here. And then our average, right, this is 0.607 times, and this is 0.707 or 6321 times the VP is the average, and then the effective, or RMS, is the 0.707 times it. Okay, so here's a table. This is a great table in the textbook, and it tells you how to calculate these values. All right, so the effective, the average, and then the peak to peak. So to get those, it shows you how to multiply that out. And this is table 14.1 in chapter 14 of the textbook. Okay, so if you're doing the homework, that's a good place to start looking at it. All right, now the next thing I want to talk about, and then I'm going to stop for now on this, is the instantaneous value of an alternating voltage is the value of voltage at a particular instant. Okay, so the instantaneous value, and it can be any value between and including the two extremes of 0 and the plus or minus the peak value. The value is related to the sine of the angle of rotation of the armature of an AC generator at a particular instant. Okay, so this is where some of that trick is going to come in, and all we need to know is how to calculate this. So the instantaneous value is just the voltage peak times the sine of the angle that it's at. So you take sine of 90 or sine of 270, where it's 1 or -1, right? That's the very top and the very bottom. And that's where you take, it's just a voltage peak, right? Because it's times 1 or -1. All right. So what is the instantaneous value of a waveform of VP of 150 at an angle of 30 degrees? So let me change my camera again. And that was the instantaneous value where VP is sine of theta, and VP was, let me go back to that. Should have wrote this down first. Slide 25. So the VP is 150 sine of 30, right? All right, so it's VP times sine of theta. So if we look at our calculator here, let me get it where I can see it. And focus, there we go. So it's going to be 150 times, and then you just hit the sine of 30 degrees. And it comes out to 75 volts, right? Hopefully you can see it. I need to find a spot where that camera's a lot, or that value is a lot easier. But here it is 150 times the sine of 30. So that's 75 volts. Okay. So when we do this, and I'm sorry about switching back and forth between the camera and the PowerPoint here, but that's the way it's got to go. So when we calculate that, it comes out to 75. So here, 150 sine 30 and then hit equals, you'll get 75 volts. So the instantaneous voltage at 30 degrees. So on our sine waves, remember, here's 0 degrees, here's 90 degrees, here's 180 degrees, here's 270 degrees, and then here's 360 degrees or back to 0, right? Because we have a total of 360 degrees in one complete circle, right? That is how we get the sine. Okay, so at 30 degrees, basically we're saying if this is 90, 45 is in the middle, so right around this spot right here, what would be the voltage there? And it would be approximately half of the voltage peak, okay? And that's based on the sine function. So you can see that there. All right, so what is the instantaneous value of a waveform of VP of 200 degrees at an angle of 345 degrees. So you would just go VP would be 200. Let me clear here. 200 and then sine 345, and that's negative 51.764 volts. What would be 200 at 30? 200 sine 30 is 100 volts. 200 sine 160 and so forth. So you can calculate those very, very easily using your calculator. So that's our instantaneous voltage. All right. And I'm going to stop right there, and or actually let me cover this part. The frequency and the period. So one complete revolution is 360 degrees, and if it takes 1 second or one revolution per second, that means it's one revolution per second. So 1/1 second, the hertz or frequency is 1 hertz. So the frequency is the number of repetitions of any periodic wave in a unit of time. And a periodic wave is one that repeats. Sine waves repeat. It's not limited to sine waves. Other waveforms are possible. So our digital, right, which is a square wave, is also repetitive, and it will have a frequency. And it's all named after the German physicist Heinrich Hertz, right? He's the one who found that relationship. Now, the period is from the max value to the next max value, or from 0 to 0, or from negative to the next negative. Wherever you measure it, as long as it's the same distance on each one, it will measure. And then, of course, the VP, and then the peak to peak, and the frequency is 1 over this time period. So whatever the period is time. Now notice the T here is capital T. The horizontal is time in the little t. Okay, so frequency is 1 over the period, which is represented with the symbol of T. All right. So in the United States, our power operates at 60 hertz, and it has an RMS value of 120 volts. So if you see this question on a test or a quiz or a homework or something, it says, if you were to take your oscilloscope and plug it into your wall, and we know it's 120 volts RMS, what is it in the peak or the peak to peak? You would have to do those calculations to test that. Now, England and Europe uses 240 volts and at a 50 hertz cycle. Okay, so that's there. Now, here are some of the common frequencies, like our sound equipment goes between 20 hertz and 20 kilohertz. That's because the human ear can hear between a low frequency of 20 hertz and a high frequency of 20,000 hertz. And if you had a set of speakers attached to your function generator and you set it on those frequencies, it would give out a value. You'd hear it on your speakers. Okay. And there's an app that if people are over a certain age, they start losing their low frequency hearing. And there's an app, I forget it's called, like an old man app or something, where you can play these sounds, and if people can't hear it, you know how old they are. They're older than, they're not a 20 something. Okay. And then there's some other frequencies here. All right. Now, the period is the amount of time it takes a waveform to complete one cycle, and the period is inversely proportional to the frequency. So a 60 hertz waveform will have a period of 16.67 milliseconds. So on our oscilloscope, we measure, remember, our horizontal is in time. So that's going to be in seconds, milliseconds, microseconds, nanoseconds, whatever it is. Okay. And then the voltage is in voltage, in some sort of value of voltage. All right. So the period equals 1 over the frequency. The frequency equals 1 over the period. So what's the period of a 350 3,500 kilohertz, you would take 1 over 3,500. So let me do that on my calculator. 1 divided by 3,500. And that will be 285 gigahertz, or nanohertz, 10 to the negative 9. What is the period frequency of a period of 120? So 1 divided by 120 microseconds, which is 10 to the negative 6. And that is 8.33 kilohertz. Okay, so you can do some of those calculations to get that all figured out. Okay, now not all these waveforms have to be sine waves, right? The same, all the conditions are the same, right? The period, the peak to peak, the peak, all of that are going to be the same, but you can have square waves, triangle waves, sawtooth waves, and in one of the labs, you'll make some changes there. All right, so I'm going to stop that right there, but I do want to pull up, let me go to my screen here. So I'm going to go to, all right. So let me open up this week's homework. All right, so hopefully you can see this. This is what you're going to get. And if you go to Canvas and you go to module week 1, and there's a web page in there that says homework 1, you can download this file and print it out. Or when you come to lab on Thursday, we'll have a copy of it there. You can pick this up. And this is a really simple lab for this week. So all I ask you is, given this scope, so I took a screenshot of an oscilloscope and I said, if it's set to 1 voltage per division and 50 microseconds per division, so the 1 voltage, that means from here, right here to right here is 1 volt. That's 1 division, 2 divisions, 3, 4. So what is the voltage peak? This is going to be 2 voltage peak. What's the voltage peak to peak? Would be 1, 2, 3, 4 voltage peak. And then the same thing here is, now we set it to 5. So this would be 5, 10, 15, 20 voltage peak to peak. And then to get VRMS, you take it times 0.707. To get the period, you will look at the divisions in the horizontal. So here it's 50 microseconds, right? So remember, milli is M, and then the micro is the mu here, the Greek letter mu. And so this is saying from 0 volts to 0 volts, each one of these blocks, this block here, this block here, this block here, or division, is 50 microseconds. So what is the frequency, or the period would be 50, 100, 150, 200, 250 microseconds would be the period. What would be the frequency? Would be 1 over the period. Okay. And then the same thing for this one. Now they're milliseconds. So that means it's 1, 2, 3, 4, 5 milliseconds. So what is the period? 5 milliseconds. What's the frequency? 1 over 5 milliseconds. So this is a really basic understanding of the sine wave, but we've got to start somewhere. So that's where we're going to go this week. So that's the information I wanted to share with you. And if you have any questions, let me show this, because probably easier to do it this way. So if I go to Canvas, so let me go log into the portal. Oh, right, so I'm gonna go to our course. So you just come to the portal, click on the Canvas slide there, and then we want to go to ELEC50B, and we come to the modules. You'll see here, this is the homework that I just showed you. So if you click on here, you can print this out if you want to work on it at home, or you can come in and pick one up on Thursday when you come to lab. Okay, so that's there. And then this video that I'm making right now will be under week 1. So week 1 here says, here's our objectives. And then the video will be right here once I'm done recording this. And then there's also in our course, there's this Ask the Professor. And this is a discussion forum that I want us to use if you have a question. So just imagine we're in a regular classroom, right? A face-to-face class, we're all sitting at the desk, and Bob has a question, he raises his hand, hey, Professor Miller, how do I do this? I'll answer him. And then there's 20 other people in the class that heard that, right? Well, this is that area on an online class, on a hybrid class. So this is where if you have a question, just come in here, click on reply, post your question, and then I'll answer it. And it will be so everybody can see it. Because a lot of times, if you have a question, there's someone else in the classroom that has the same question, so it helps them. That's what this is for. So this is kind of like our public forum, or hey, where's this? How do I do that? How did you do this in the video? How, all that. That's where we'll have this interaction and we'll be able to do that together. Okay. And then of course the PowerPoints are here. And then here's that video I mentioned with Edison versus Tesla. All right. So that's it for week 1. If you have any questions, reach out to me, put in the Ask the Professor forum, and we'll get going, and away we go. And I'll see you on Thursday night, that first week. I'll be there for the lab, along with the lab instructor, Professor Alagi, and we'll get you lined up on what you're doing all the way through. All right, take care. Bye.